Okay, so here we go. The first chapter is called Chapter E, not even Chapter 1. It provides you with a background for science. You need to learn how to deal with data, and data is all over chemistry. And so this first chapter is called Units, Measurement, and Problem Solving. So you need to learn how to measure properly. There are rules. You may have heard of significant figures. It's all about how to measure properly and manipulate data. And you're going to have to learn that everything has a unit. And if you develop these good habits, you're not going to make mistakes. And you're going to become maybe a good scientist, or maybe you're just going to survive Chem 1 and Chem 2 so you can move on to organic chemistry or whatever your plan is for the future. But units are important. So if you're converting dollars to cents, it's not just 100 cents is the same thing as $1. You can't just write down 100 equals 1, right? You have to have units here, right? So you have to always write down, even if it's obvious, that this is cents and this is dollars. Okay, now that's a unit. And when you convert, you have to include these units. They have to be multiplied or divided depending on what you're doing with these numbers. So this is pretty important, right? And so the author chooses a real-life example where a mistake in measurement cost somebody $125 million, and that somebody was the taxpayer, right? So because NASA, back in 1998, they launched a Mars climate orbiter, and one of the engineers used the wrong measurement. He used pounds instead of newtons, okay? And so you see the difference here, right? So a pound is about 1/5 of a newton. And so what happened is, because a newton is a force, right? And so the newton is measured in kilograms times meters per second squared. And a pound is a different measure of force. Anyway, it cost $125 million because what happened is they miscalculated the force that the Mars would exert on the lunar module, and therefore the estimated trajectory wasn't true, and the lunar module crashed on Mars. And that's not a mistake you want to be making, right? Okay. So what's in store for us? Again, units are so important, right? It's a fixed standard of measurement. If you are measuring the length, is that in meters, centimeter, or is it in miles, right? That's a measure of distance. Is it in yards? And so that's important that you communicate that. And then we want to distinguish between, of course, as a scientist, you want to be precise and accurate. That's important to be both. But there is a difference. Precision is just how close are your measurements, how consistent are you with your measurements, and accuracy is how far off, or are you actually taking measurement of what you are seeking. If you are weighing a coin that we know weighs 2.5 grams, if you weigh it on a balance and it says 3 grams, then you're not accurate, then you're off. Okay, and so that's actually nicely portrayed here, the difference between accuracy and precise, by this shooting target here. It comes from my forensic chemistry book. I thought it's more fun than the dartboard, right? If you're trying to shoot the criminal right in the heart, and then this was accuracy and precision, because all your 4 measurements, all your 4 shots are right where you want to hit the dude, right? So this is precise and accurate, and so this is really what you're after. And you want to measure the same way if you weigh something, or use a graduated cylinder to measure the volume of a liquid. You want to be doing it both accurately and precise. Now, one of the problems is if you have good precision, right? If all your measurements, like here, I mean, that looks like a good set of measures, right? They're all in the same vicinity, right? They're close together, which is great, but you don't notice that you're actually way off from your target, so you're not very accurate, and sometimes you don't know that. Of course, this you will be able to see if you take the measurement several times and you're all over the place, like here, you know, a shoulder, the other shoulder, and the stomach, and in the head, instead of right in the middle. Your average may still be right in the middle, but you're not accurate, you're not precise. So that's the difference between accuracy and precise. And normally what's used in chemistry textbook is the target analogy, which works very well. All right, so here we are looking at probably laboratory measurements of some students that were trying to measure a block that weighs 10 grams. So we know, the instructor knows this weighs 10 grams, and so the students go to the balance and they weigh that block 4 times, right? So there are 4 trials here, and then they calculate an average. And so if you look at student A, and if you just look at the average, you might think that's not bad, right? So that's pretty close. It's not super accurate, but it's close. But if you look at his different measurements, the range is from 9.8 or 9.78 all the way to 10.49, which is quite a long range. It's a range of 0.7 or so, and so he's not very precise, and so you cannot really trust this average. And student B is very precise here, right? All of his measurements are within, but it's very precise. But he's actually way off with this average. So he's precise but not accurate, and this guy is neither precise nor accurate. And student C is very accurate, right? He's got almost a perfect average, and his range is just between 0.05, right? So that's a very narrow range, meaning it's very precise. So I think you get the point. So how do you measure? It depends on your measuring device, right? If you're measuring the length of something, let's say this paper clip, and your ruler here, the device you use to measure, only gives you the nearest, the measured line of a full centimeter and nothing in between, so just whole centimeters. All you really know is it's somewhere between 1 and 2, right? So you know it's at least 1 centimeter. It's not 2, and it's not really, and then you're starting to guess, right? So you know for certain it's 1 point something, right? And what you do is you take an educated guess, right? So you have a digit of certainty, and then the very last digit, this goes for everything, and you have to report that digit. Okay, it increases your accuracy and your precision. So some people may look at that and say, well, it's definitely not, oh, I'm sorry, that's 2, right? Oh, that's just great, right? So obviously it's 2 point something. And it's not 2.5, and it's maybe 2.3 or 2.4, and you know what, 2.3 centimeters, that's perfectly fair here. 2.4 centimeters is just as fair. That's somebody else's educated guess, right? So we know for certain it's 2, and then it's up to you. How do you look at that? And that's your data, and so that just implies that the last measurement, the last number is a measure of uncertainty. Now, if we have even the 1/10 of a centimeter here, so we have 1 as increments, then we become more accurate here, right? So now we know it is 2 point, and so this is 1, 2, 3, so it's 2.3, and somewhere between 2.3 and 2.4. Now, this is really important that you don't just leave it at 2.3 and decide that, oh, this is too hard for me to guess in the middle. No, you always have to guess, right? And so if you either think it's right on the dot or it's exactly in between, then you put 2.35 centimeter if you think it's exactly in between. If you think this is right on the dot, which in my opinion it is not, you must put 2.30 centimeters. You need to don't leave that 0 off, because now you have 3 measured figures, 3 significant figures. It's important, okay? And so if I had to actually put a measurement there, I would say this is not really, it's 2.34 centimeters, Okay, I don't think it's right in the middle. And then that's up to me, and it's up to you. Again, so all of these are okay. Although I think that most of us will agree that this does not exactly line up with a 0. So that I think we can rule out. And 2.34 centimeters. So you get 3 significant figures, where now this last one, that's your measure of uncertainty. And this is true for any measuring device that you use. Graduated cylinders, right? If I was to extend this and has a base and you pour a liquid into it, it measures volume. Okay, so it measures the volume of a liquid. And so first of all, you need to learn how to read it. Okay, so here we have the increments are, if this is in milliliters, okay, 4 and 5 are milliliters. It is somewhere between 4.5 and 4.6. Okay, so the first thing is you need to read this, like, it's anywhere from here to here, right? But you read this at the bottom of this meniscus here. So in the very center, this is where you want to read it, okay? And so it is 4.5, and it's almost on that 4.6. But in my opinion, so it's 4.59 milliliters, in my opinion. Okay, so that's the way I read it. Or somebody else might say, nah, this is right on the dot, so then it would be 4.60 milliliters, or maybe 4.58 milliliters. Okay, and that's how you read a graduated cylinder. This is a burette, and you will use this for Chem 2, probably not for Chem 1, especially not the online version, but you fill it. It usually goes to 50, to the 0 mark, and then it has to be filled like this, where the 0 needs to be lined up with the meniscus needs to be lined up with that 0, and then as you add it drop by drop, there's a little valve here. You can add this drop by drop. Let's say you have a base and an acid, and you're adding it slowly to neutralize it, and you have to stop at a certain point, and you want to determine the concentration of the solution. So that's when you want. Let's say you drain it drop by drop, and then you stop, and so you have the final reading minus the initial reading. That gives you the volume of the substance in the burette that you've added. It's read the same way that you read a graduated cylinder, except you have from top to bottom. So here you have 10 and then 20 milliliters, and so it's somewhere between 24, so it's like 24 for sure here, right? So it's 1, 2, 3, 4. So it's a little bit below the fourth one. So it's 24 point something. Let's say 24.1 milliliters. Again, this is the last digit you have. It's important that you guess. Even if you don't think you can read it, then you need to put a 0. If you think it's right on the dot, put a 0. And that's how I expect you to measure, and that's how every chemistry teacher will expect you to measure. All of your lab teachers will expect you to do that this way, right? Okay, so that was volume. Now we're going to look at if you put something on the balance. We've got the same phenomenon, right? And a lot of students will put something on the balance, and a lot of times we have these balances, they go out to like 100 to like 4 or 5 digits. This one goes out to 4 digits behind, so it's 1/10,000th of a gram, which is pretty great. Whereas this one is just 1/10 of a gram. But usually, what happens is this last number goes up and down. It never stops, right? So this is a picture, so 10.4977 grams. That's fine, but this last number will fluctuate between 8, 9, and even go down. And so you just write down what you see, right? So sometimes it's a 6, sometimes it's an 8. So you write that down. It is understood that that is actually an uncertainty. Okay, the wind may blow or something, and it just fluctuates sometimes here, right? So this balance here on the left measures to the nearest 10th of a gram. So we write that down, 10.5 grams. We have 3 measurements here, 3 significant figures, and that's how that reported. And so the same mass of these blue crystals, which are probably copper sulfate, they are measured more accurately here by this balance, and so you can see this is okay. If you were to round that up, it would be 10.5, but you don't want to round that up. Okay, you want to use every single one of those numbers. This gives you 6, 1, 2, 3, 4, 5, 6 significant figures. That's really good. And so that's what you want to stick with. What your device gives you, the best you can do. Okay, so base, SI, scientific base units, they go back a couple hundred years. And so a length is always measured in meters. Okay, and that's because Europe was trying to, when science really took off a couple hundred years ago, they wanted to have some sort of regularity and be consistent throughout the scientific communication and amongst the scientists. So they came up with these standards, right? And so originally the meter was actually supposed to be 1/10,000,000th the distance between the equator and the North Pole through Paris. Okay, and so they just made that, okay, that's going to be the meter. And so there's actually a meter in a museum, same with a kilogram. There's some metal cylinder that they say, okay, this is just going to be a kilogram. And so measured that and then replicated that, and that was a kilogram. And so what is unusual about the kilogram is that it actually contains a prefix here. Right? The meter and the second here and Kelvin, mole, ampere, and candelars are all standalone units, but the kilogram actually has a prefix. So, but that actually is a factor of 1,000. Okay, so gram is something pretty small. A gram is 1/1000th of a kilogram. So if you take that cylinder and you cut it up into 1,000 pieces, you would have a gram. Okay, so keep that in mind, that the kilo here, the little k, is actually prefix, and we're going to look at that in a minute. Whereas this is C is not a prefix. This is part of the luminescent intensity. We will not actually use that at all. It's just an example that the author uses. You can actually flip through the pages and look at that as we go. Okay, so you know how to measure. Let's just take a look at if I give you a measurement and what numbers are important. What is your measurement and how many significant figures are there? So those digits that are actually measured. Sometimes there are zeros that are there for necessity, but they're not actually measured. Okay, sometimes zeros are measured, so we need to look at these rules here, right? So 12.5 centimeters has 3 measured figures, right? So the 1, 2, and 3, where we know again, and the unit is so important, always have that unit there. Centimeters has to be there, and so we have 3 significant figures, and here we have an even more accurate device that we use to measure the length in meters here, 7.365 meters. Well, it's not more accurate, but anyway, we have 4 significant figures. Okay, so it becomes a little confusing sometimes if there are zeros, right? For example, if you have 0.01 centimeter, you actually just have one significant figure, right? These zeros are just there as placeholders, and so that becomes, whereas if you have 1.01, then that 0 is significant, let's say grams, and you count that as 3 significant figures. So all digits are significant except zeros at the beginning of the number and possible terminal zeros. Okay, so here are zeros at the beginning of the number here. The first number is 1. That's that example. Terminal zeros ending at the right of a decimal point are significant. Okay, so there's more to it. You have to have a number, a decimal, and then a 0, and that makes that 0 significant, even if there wasn't another number there. Terminal zeros in a number without an explicit decimal point may or may not be significant. Okay, all right. Let's just take a look at some examples here, right? So here we have 20,567 grams. Every single one of those numbers is measured. So zeros in between numbers are always significant. So we have 1, 2, 3, 4, 5 significant figures. 5 sig figs. 75.0 miles. Well, if it was just 75, we wouldn't need that 0 there. So the 0 behind the decimal in this case is significant because it follows not only a decimal, but also there are numbers in front of it. So this is 3 significant figures. And you will lose points on an exam if you don't do that properly. Here we have 0.00376 ounces. Well, the zeros that are in front of a number here, they don't count even if there is a decimal here, because there is no number before that first zero. Before the decimal, there's no number. These are just placeholders. You can't eliminate those zeros because it would change the magnitude, right? You can't just write 376. That's completely different than 0.00376 ounces. So here we have also 3 significant figures. 2.4006 liters. Okay, so here we have a number, a decimal, and then a bunch of numbers and zeros. And so those zeros count whether that 6 was there or not. So we have 1, 2, 3, 4, 5 significant figures. And here we have an astronomical temperature, 157,000 degrees Celsius. That's pretty hot. That's irrelevant how hot it is. What we're looking at are the numbers. Again, you have to have these zeros there. And since there is no decimal here, we don't know if those zeros are measured or not. That's what this rule here was trying to tell you. Terminal zeros are in a number without an explicit decimal point. May or may not be significant. Okay. Well, if it's may or may not, we go with let's not. Okay, so these are most likely not measured. It's an estimate. So we just have 3 significant figures. Okay, so hopefully that's clear. And then what we can do is we can report our number in scientific notation. Okay, so some of you may know what that is, some of you do not. What we are going to do is we're going to clarify, and this becomes especially important for a small number where we've decided that 0.0310 has 3 significant figures, and in order to avoid all confusion, we write it differently. We move this decimal by 2, which changes this number to 3.10. So we know that 0 is significant. We have 1, 2, 3 significant figures. And this is just a factor, right? 10 to the negative 2 is just 1 divided by 100, right? So 10 to the 2 is 100, and a negative means 1 over, right? Okay? So that means that in order to get back to the original, we have to multiply it by a factor of 10 to the negative 2, okay? So this here is the same thing as that number. If you wanted to express a larger number in scientific notation, like here we have this 0 that's not significant, we can make it go away by moving the decimal here 1, 2, 3 to the left. So that's 10 to the 3, okay? And since we make a larger number smaller, right, 3.01, 10 to the 3 is 1,000. Okay. I'll assume that you know what 10 to the 3 and 10 to the minus 3 means, and 10 to the minus 6, 1 millionth, 10 to the minus 7, 10 million, and so on and so forth. That's important that you need to know that. Refresh that, practice that. Okay, well, so these are the same numbers that we just looked at for significant figures, and here they are reported in scientific notation. So this was moved over 1, 2, 3, 4. That's where the 4 comes from. So you move it to the left, you have a positive 4. Same here, you move it 1 over, so 7.5 times 10 to the 1. And now we're going to move the decimal to the right, and then we get a negative, right? So 1, 2, 3. So it's a negative 3, or 1 over 1,000, right? If you divide 3.76 by 1,000, your calculator will tell you 0.00376. Simple as that. This number is already the way it needs to be. It has 5 significant figures. I mean, it's 10 to the 0 is 1, right? So you don't really need that, but just you can if you wanted to. And here this is great example because these 3 zeros are not significant, and so we move this 1, 2, 3, 4, 5, so it's 10 to the 5 degrees Celsius. All right, it's really not that simple. I mean that complicated. Just practice a few times. One of the labs deals with it. Okay, and then the first thing when you have, we're going to manipulate data now, right? So first you determine all of your data, all of your measured numbers have to be assigned as significant figures. And then sometimes we determine density, which is you take you weigh something, it weighs 40 grams, and you divide it by its volume. So you take grams divided by milliliters, and you have two different numbers, and so you got to follow rules. What happens? So multiplication and division has different numbers than adding and dividing. And rather than reading this, and yeah, you got to worry about rounding too. I'm going to just work a couple of examples and to make it clear to you here, okay? So here we measured, let's say we measured some sort of area, like a sheet of paper, okay, or a piece of paper here, really, right? And so you must, the person who measured this must have used two different rulers, or it was very sloppy. But so here your first measurement, 3.56 centimeters, gives you 3 significant figures, but then he measures the length and it's just 4. Okay, now that's your weakest link here, right? So there's only one significant figure. So when you multiply and divide, your answer can only have one significant figure. That's going to make things a little tricky. Okay, so your calculator will tell you 14.24, but you cannot do this, right? So you can only have one significant figure. So this gets all rounded down to 10. And of course, it's, you see here you have centimeters times centimeters. This is why units are so important, right? A centimeter times a centimeter is a centimeter squared. Okay, a centimeter divided by a centimeter is nothing. Is 1, and that unit will be canceled, so then there wouldn't be a unit. But that's important that you write the units down, and that you also apply the multiplication or division or subtraction, whatever it is, the square root, to the units. Okay, that's a habit you should develop. So then this is reported as 10 centimeters, where we know that that one is not significant. Or if you wish, 1.0 times 10 to the 1 centimeters squared, right? Okay, so the next one is another multiplication, so milliliters times milliliters, so we get milliliters squared as the unit, and we have 4 significant figures and 2. And so now your answer needs to be shortened to 2 significant figure. Now here, if you write, you want to write 10 as well. Ooh, a glitch. All right, you want to write 10, but that 0 is significant, so you can put a decimal here. Or to make it even more clear, you just put 10 times 1.0 times 10 to the 1 milliliters squared. Now there's no ambiguity here. This may be a little weird to have 10 and with a decimal there, right? Okay, so this is all multiplication and division. 2 more examples for that. I'll shorten that. Again, we have 3 significant figures and 1, so your answer cannot be 5.0. Your answer is just 5 centimeters. And so centimeter divided by centimeter, that should go away. So that is incorrect. Anyway, so and now we have, so the only measurement here is 4.5. Everything else is a conversion factor. So we're going to report the result with two significant figures. Okay, so this one may be a little bit tricky because there's like, hey, there's a 1. Well, that's an exact measurement. There's always 12 inches in a foot, right? And so there's always 2.54 centimeters in an inch. So you got to focus on your measurements here, and everything is multiplied and divided, and this is exact as well. But we're not quite there yet. We're gonna go over that. So a lot of times when you're just converting from one unit to another, the only measurement you have is your original measurements, the 4.5 feet, which was measured to 2 significant figures. So your answer will also be and 2. That's multiplying and dividing. You just simply look at your weakest link. 1, so you only get 1, and so on and so forth. For adding and subtracting, we look at how far out do all of your measurements go out, and do they have that in common, right? So if you take 23.467 inches and you add 313.21 inches to it, you simply say, well, I measured to the nearest hundredth of an inch every time. So that's how far out I can report this answer, right? I didn't do that for the 313.2, right? So when you add that up, you're going to have to lose this last one, right? And so you need to round that up, and that's exactly what happened here. 336.68. So you have actually 1, 2, 3, 4, 5 significant figures in your answer, which has absolutely nothing to do with the fact that you have 5 significant figures in each of these. It has something to do with how far out each of these measurements go, okay? Like this one here, you're going to lose a lot of accuracy here because your first measurement, 457, doesn't really go further than just the nearest centimeter, okay? And whereas what you're subtracting here is a fraction of a centimeter and measured very accurately. But so you have to report that just to the nearest centimeter here, right? So 456.32 gets rounded down to 456 centimeters. Okay. All right, let's take a little break. And if you still have energy, you can start the next video.